Okay, so tape is rolling there. Since Amanda asked me a question about taking the final exam, and so let me answer this for everyone. It applies to some other people too. So, so this is in the syllabus, right? So if you read the syllabus, remember, if you have 75 flux dollars at the end of the semester, you can take the average of your 3 midterm tests and use that to replace the final, so you would not have to take the final exam. If you were happy with the average of the 3 midterms, you wouldn't, as your final exam score, you wouldn't have to take the final exam. So, but you got to have 75 flux dollars. So you need to look at your flux dollars total. For some of you, it's pretty high. So for some of you, you do have the opportunity to apply this option if you can get to 75 by the end of the semester. Now, we still have the third test. So if you made an A on the third test, for example, you could earn 15 flux dollars there. If you made a B, you could earn 10 flux dollars. You still have your attendance to add in, which if you have not violated the attendance policy, that's 25 flux dollars. And you have your homework. I forgot about that. So if your homework average is high enough, that also adds flux dollars. You'll have to look at the syllabus. Huh? I forgot what the specific cutoffs are, so you need to look in the syllabus and see what that is. They're slightly different than for the tests. Yeah, Iris.
So I have a question.
No, the attendance dollars will not be added till the end because I don't know what your attendance is yet, right? So, so those have not been factored in, okay? And then the homework dollars have not been factored in, right? Okay. Plus then possibly that third test. And remember, you can earn $2 a week for going to the center. It's only $2 per week, not per visit. But you still have this week, next week, and the following week. So you can still earn $6 that way. And Zoom counts, right? So you can make virtual visits. So you could pull together $6 also that way. Towards your flux dollars total. Yeah, Jen. If you are 4 and below, then you are okay, right? That's what the syllabus says, I think. So you need to you can check with me about what I have counted as your attendance so far. I think yours is quite good, right? I don't recall you being absent, so.
You can see us on Zoom. Oh, it does?
Yes, that's right. Yeah, Zoom, I account for that. Yeah. So now remember the exception to that is if you were not doing well on the test and you were required to come to class, but you were attending Zoom and you had not, sometimes people email me with exceptional situations. But otherwise, if you didn't email me and you were supposed to be in class, but you were on Zoom, that's good, but you won't get counted for your attendance that way, right? Okay. So keep that in mind. Now, even if you don't earn the $75 to test out of to place out of the final exam, remember there are other things you get for your flux dollars. So it's still worth accumulating flux dollars here, even at the end of the semester, because you can. There are other options, right, for expending your flux dollars. So keep that in mind. That's all in the final. I mean, that's all in the syllabus toward the end of the syllabus, right? I wanted to show you that if you go to my total. So I don't know, is this the fastest way to find it? If you go to my total, and then you have to look down here to raw scores, it will show you your current flux, okay? Don't pay attention to the maximum possible, just see what the score is. That would be your current flux dollars, okay? So I think some of you are in the 40s, I think, already, okay? So, but even if you're not going to make it to the 75, again, as I mentioned, there are other things you can use with the flux dollars. So it's still beneficial to earn them here at the end of the semester. Now, I have posted the sample test for test number 3. So that is posted. right? And so, one thing you could do, right, is take the sample test and go to the math center and get assistance with working on the sample test, right? And so you can earn flux dollars that way. Of course, I won't post the answers immediately, right? But the sample test itself for test number 3 is posted in the usual spot on Blackboard. The test is 2 weeks from today, okay, May the 4th, which is also the last day of regular day of class. The final exam is the following week, May the 11th, I think. I'll have to double check that, but I think it wasn't. They didn't have the final exam schedule at the beginning of the semester, but they have since posted it. I think it's May the 11th. It will be just at essentially the regular class time on May the 11th. There might be a slight difference of 30 minutes. The final exam periods are slightly different, but it's essentially the same class time. Okay. So if you are, looking to improve your grade, right, here, not just maintain your grade, but improve your grade toward the end of the semester, then work on that sample test, right? Okay, make sure you work on that diligently. And you can go to the Math Center, North 925. They can help you with that. Or make sure you finish your homework now between now and the end of the semester, right? So you can have your homework average as high as possible. And of course, come to class, right? It's just the usual thing. Yeah, Giselle, May the 11th, I think, is the final exam, but I'll have to double check that. It's posted somewhere on the university webpage, but when the final exam is for this particular time period, but I think it's May the 11th. Okay, so we have a homework that's due not tonight, but Friday night. But so let me open that and look at it just briefly here. Do y'all have any questions particular that you want to ask about that homework? So this is solving exponential and logarithmic equations using the idea of inverses, of course, because exponential functions and logarithmic functions are inverses of one another. So it's kind of similar to the homework that was due Monday night on solving trigonometric equations, right? Where you're also using inverses, but you're using inverse trig functions. Number 7. Well, maybe that was one I was going to mention. Yes. Okay. So I'm glad you asked that one because that was one that I wanted to talk about anyway. That one's a little bit harder. Yeah. And that's probably the hardest one there, except possibly for number 9, except we did an example like number 9 in class last time. So if you're having trouble with number 9, go back and look at the video for the class last time. We did a recall practice that's very similar to this problem. The recall practice involved virus particles, right, and taking medicine. So scroll through that recall practice until you find that particular problem and watch that again. Scroll through the video, until you find that particular recall practice, and then look at that, and then maybe that can help you with how you're going to do problem number 9. It's very similar. All right, now we did also do a problem similar to 7, but not quite as difficult as 7. So let's look at this one. Let me lower the screen then. Remember what that problem is. So natural log of x minus 4 plus the natural log of x plus 5 equals 1, and your version of the problem might be maybe slightly different. Let me scroll to the bottom of the notes that we're going to look at today and see if I can find some blank paper. Here you get a quick preview of coming events there. Let me scroll to the bottom here. So let's see, what was that natural log of, what was it, x? Was it x minus 4? Plus the natural log of x plus 5 equals to 1. Okay. All right. So we know sort of what the basic strategy is, right, for solving these equations that involve logarithms. At some point, we want to apply the inverse function, which is the natural exponential function e to a power, right? So at some point here, we're going to raise both sides. We're going to raise e. Got to say this in the proper order. We're going to raise e to both sides of the equation so that we can eliminate the natural log from the equation, right? But we have to do a little bit of prep work first, because before I raise e to both sides of the equation, I want only one logarithm on one side, okay? So here I've got this, I've got two logs, right, on the left-hand side. So I want to combine those two logarithms. And remember, we can do that now through one of our logarithmic properties. Remember, if you have the sum of two logarithms, like we have here, right, log of this quantity plus log of the second quantity, you can combine those as the log of what? So how do you put these two things together? Yeah, that's a product, right? Sorry, okay. So in other words, you just have log of the product of those two things, okay? Right. When you see this property that we're using here stated, it usually is stated in the reverse order. You'll be told, oh, if you have log of a product, that's the same as sum of the logarithms. But usually it's more useful in this order, where you have sum of logarithms and you want to write that as a single log of a product, like we do in this example. So a natural log of x minus 4 plus natural log of x plus 5 is the same as natural log of x minus 4 times x plus 5. All here still equal to 1, of course. See, now we're in the situation where we want to be, okay? Because now we can apply the inverse function, which is the natural exponential function. So I can raise e to both sides of this equation, okay? And what happens, of course, here on the left-hand side is these things essentially cancel each other, right? Because they're inverses. So you end up here with just x minus 4 times x plus 5 equals e. Now, e to the first power, which is just e. Remember, e is a number, right? Okay, it's an irrational number, approximately 2.718, etc. But it's irrational, so it has a non-terminating, non-repeating decimal. So it's not convenient to write it out as a decimal. That's why we use this special symbol e to represent that number, just like we use pi to represent 3.14159, etc. Right? Pi is also an irrational number. Okay, so now we've got this equation to solve. Now, that's still kind of a formidable equation to solve, but it doesn't have logs in it. So we've made some progress, I guess, right? Because logs are going to be tricky, right? So now we want to see if we can solve this equation. All right, so here's what I suggest doing. It's too bad that this is not x minus 4 times x plus 5 equals 0, because if you had x plus 4 times x minus 5 equals 0, right, you would have a product equaling 0, and then you would just know either x minus 4 is 0 or x plus 5 is 0, okay? When you say minus e, we are going to set this to 0, okay? Yeah, by subtracting e from both sides. Yeah, so exactly what you're suggesting, Amanda. I was just pointing out that this equation is a little bit more difficult, right? Okay, than having a 0 here on the right hand side. Here's what you do not want to do, however. Okay, so please do not write x minus 4 equal e or x plus 5 equals e. All right, that is not correct to do that. Okay, that would be convenient if that were true, but that's not true. All right, so don't make this mistake, right? Okay, so what are we going to do? Well, what I suggest in this case is try to simplify. And so by simplifying, I mean go ahead and multiply out the x minus 4 times the x plus 5 and set the equation to 0. So to set the equation to 0, you can do that, as Amanda suggested, by moving the e to the left-hand side. Right? Let me show you why it's convenient to simplify and set to 0. So if you multiply x minus 4 times x plus 5, you get x times x is x squared, and then you have plus 5x, right? Plus 5x, and then minus 4 times x is minus 4x, and then minus 4 times plus 5 is minus 20, right? And then we're going to subtract e also. So we have this. All right, so let's add those two middle terms together. So I get x squared what? Plus x, and then minus 20 minus e, right? Equals 0. That is a quadratic equation, okay? So that's a quadratic equation because that involves x squared, right? Now, so what strategies do we have for solving quadratic equations like this one, right? Where you have that x squared term in the equation. There's really only two. So what are our choices here? We can try to do what? What can we try to do with the left-hand side here first? Factor, but we're not going to get very far in the factoring because of this 20 minus e here, right? Okay, so that's going to make the factoring tough. So if we can't factor, then what's plan B? The quadratic formula, right? So we can use the quadratic formula when you have an equation set equal to 0, make sure it's set equal to 0, where you have the unknown squared, like here, x squared, that's a quadratic equation, and you can use the quadratic formula. Remember, today we were talking about equations where we had, or last time we started talking about, and we're going to continue talking about today, equations where the unknown is raised to a power higher than 2, like x cubed or x4. Of course, those are just that much more difficult, right? But for a quadratic equation, you can always use the quadratic formula. So you must always remember that, right? You can always solve, this is a second degree equation because you have the unknown squared. You can always solve those, all right? You can either do it by factoring. You can't do it by, there are other methods too, but the two main ones are factoring. You can't use factoring, then you can always rely on the quadratic formula. So let's, first we got to remember the quadratic formula, right? So the quadratic formula says, oh, solutions to equations like this one, they're going to be what? Minus b plus or minus the square root of b squared minus 4 times a times c, all of that over 2 times a. And you just have to recognize what the a, b, and c are, right? And then plug them into the quadratic formula. What is the a here for this equation? 1, right? That's the coefficient of the x squared. So that's 1, easy. What's the b? 1. Yeah, also easy. That's the coefficient of the x. So here we just have 1 times x. And then the c is the constant. So here, be careful, all right? This whole quantity at the end is going to be the constant, including the minus sign. So the c is going to be minus 20 minus e. All right, so don't forget to include that minus sign with the value of c. So then you just have to fill it in, and then you're probably going to have to use your calculator right, at some point. So we get what? Minus 1, because b is 1, right? Plus or minus the square root of 1 squared minus 4 times 1 times, and here's the messy part, that ugly c, which is minus 20 minus e, all of that over 2 times a, which is 1. So I get minus 1 plus or minus. You have two solutions here, right? One is plus the square root and one is minus the square root. What's under this square root? Let's see. 1 squared is 1. Of course, minus 4 times 1 is still minus 4, right? So you have minus 4 times minus 20 is plus 80. And then minus 4 times minus e is plus 4e. So you get a really strange number under the radical. So you really need your calculator to help you with that, right? But it's going to end up being 81 plus 4e. And then don't forget you're taking the square root of that. All of this over 2. So there's the exact, there's the two exact solutions to that equation. Can someone give me now what these two things are approximately? Can y'all use your calculator to do that for me? What's 81 plus 4e, and then you take the square root of that. It's going to be a little bit, it's going to be a little bit more than 9, I think. Something like 9.2 or 9.3, and then add a -1 on it and then divide by 2. Don't forget you have to do plus or minus that. What's just the square root of 81 plus 4e? $9.59 seems a little bit large. Don't need to do that. Huh? Uh-huh. 9.59. I was thinking that sounded a little bit large. But I may be wrong. Let me try it again. Oh, you're right. So I guessed wrong there. So, all right, so that square root is about 9.59. So we have -1 plus or minus 9. Actually, it's 585 to 3 decimal places divided by 2. So add -1 to that, divide by 2, and then subtract this from -1 and divide by 2. And what are the two answers that you get there approximately? Four point what? 293. And then the second one is something negative, right? Negative 5.27 or something. 29. Minus what? 5 point what? No. I don't think so. I got minus 5.293. So minus 5.293. So 4.293 and minus 5.293. Okay, I think those are the two approximate decimal answers here. Look, now, in this equation, you have to be very careful, though, to look at your answers, at least partially check your solutions, because look what's going to happen if you try plugging in the 4.293 back into the original equation. You get natural log of 4.293 minus 4 plus the natural log of the 4.293 plus 5 equals 1. Okay. And 4.293 minus 4, that's okay, because that's 0.293, right? So you have natural log of 0.293, whatever that is, plus this natural log of 9.293, whatever that is. That's supposed to be approximately equal to 1. You can check that with your calculator and see if that comes out to be close to 1. Does it? Did y'all try that? Okay, so I think this one we got. All right, so there's one solution. But if you try the second solution, notice what's going to happen here. If you plug in the minus 5.293, at first it all looks very innocent. when you plug in the minus 5.293. But it's not, because minus 5.293 minus 4, that is a negative number. You cannot take natural logs of negative numbers. If you try that with a calculator, you'll get an error, right? So you cannot take natural log of negative numbers. The natural log of the natural log function's domain starts at 0, but does not include 0. You can also not take natural log of 0. So this is not really the minus 5.293, although we had to work hard at that, right? That is an extraneous solution. That's not really a solution to the original equation, okay? So you have to be careful sometimes about solving log equations. When you solve these log equations, go back and just, you don't have to carefully check your answers usually, but partially check your answers. Make sure that when you plug in one of your solutions into the original equation, you're not trying to take natural log of 0, or you're not trying to take natural log of a negative number, because that's going to give you an error. Let's see if we did this right. So we think we did, right? 4.293. Let's see what the oh my gosh, it's 4 decimal places. Okay, that's a little bit ridiculous, but well, I don't know what the other decimal place is, so let's just try 0. I think it was 4.29. 4.29. Maybe it was 2.5 or something. It was. Okay, so let's submit that and hope for the best. Maybe it'll give us the right answer. Oh, yay. Okay. All right. It's good to read instructions carefully before we started working the problem and start throwing away decimal places, since they want so many decimal places in the final answer there. Okay, no, so notice, right, we didn't have to enter in the 5, right, the minus 5 answer, because that wasn't really a solution. Okay. All right. So Amanda missed all of that. That was Amanda's question. Okay. Well, she can see that on the video. All right. You guys at home have questions on this homework? This is your last chance, since it's due on Friday. So what? All right. Okay. Let's switch back to the notes then, and continue where we were last time. And remember, last time we were trying to solve more complicated equations in the process of finding roots or zeros or x-intercepts of polynomial functions. So we were working on this example where we were given this polynomial function of degree 4. This is a polynomial of degree 4, and we're just asked to find its zeros. That means its x-intercepts, also called its roots, or also called its x-intercepts, right? So we have lots of terminology there for x-intercepts of a polynomial function. And so we went through the usual routine, right? We took the formula for the function, set it to 0, right? Because that's how you find x-intercepts for any sort of function, including polynomial functions. And then we were left with trying to solve this equation. And we said this is a 4th degree equation, not a quadratic equation, right? Because it has terms higher than x squared in it. And so right now, our only strategy for solving such an equation is by factoring. And we hope we could factor that expression minus 2x to the 4th minus x cubed plus 3x squared. And so it actually turned out happily, you can start factoring by factoring x squared from all 3 of these terms. Actually, I was going to factor out a minus x squared instead of positive x squared, so I could make this leading coefficient positive. So I factored out minus x squared from all 3 of the terms, and that left us with minus x squared times 2x squared plus x minus 3, right? Now, once we did that partial factorization, that leaves us with lots of options for finding the x-intercepts now for this equation. But one thing you immediately recognize now, see, is here we have a product equals, thank God it's not e this time, right? Here we have a product that's equal to 0. And so we know then that one of the factors is 0. So either minus x squared is 0, or, of course, the other possibility is 2x squared plus x minus 3 is equal to 0. One of those two factors has to be 0 because we have the product equals 0. And so now these equations are going to be easier for us to solve, right? This one is very easy to solve. What's the solution to that first equation? You can just solve that one by inspection. X has to be what here? You're going to square some number and get 0. What's that number going to be? 0, sure, right? Okay. So you can immediately see x equals 0 is the solution to that first equation. So see, we already have one solution to the equation 0. So we've got one x-intercept already. The graph of this function crosses the x-axis at x equals 0. How many places, by the way, might it cross the x-axis? How many x-intercepts might it have? Because this is a polynomial, right? So we know something about x-intercepts of polynomials. How many polynomials might this? I mean, how many x-intercepts might this polynomial have? Four, right? Because why, Sonny? The degree, right? The degree is 4, right? The highest power of x in this polynomial formula is 4, right? And so the degree is 4. So that tells us we can have at most, maybe not exactly, but at most 4 x-intercepts, right? So we found one of them already, okay, of the 4 possible. Sonny, along the same lines, how many turning points might the graph have? 3, right? Okay, maybe none, but it could have up to 3 turning points, okay? All right, now, so let's try to find the other x-intercepts. Of course, they're going to come from this equation, but this is just a quadratic equation, right? And so, as we just practiced, we know we have foolproof methods of solving quadratic equations, right? We can either factor, or if at worst, we can use the quadratic formula. So if we have to resort to the quadratic formula, we can use that. But we're not going to get stuck here, right? We know we solve this equation if it has solutions. Quadratic equations don't have to have solutions, by the way. All right, but if it does have solutions, we know how to find them. Let's try factoring it. So that's what y'all were doing in class last time, and most people had managed to factor that one before we left, but then we didn't get to finish the problem. So I think this factors as 2x times x, right? Okay, and then I think there's a -3 here and a +1 here. Do y'all have that in your notes still? Well, we can check this. 2x times x is 2x squared. Of course, -3 times +1 is -3. So we got those two terms correct, right? And then for the middle term, we would have 2x times 1 and then -3x. Well, that's 2x minus 3x, which is, whoops, that's wrong, right? Yeah, I was thinking there was a minus sign there, but so this one is plus and this one is minus. Now, okay, so that makes it work. All right. So there's the correct factorization for 2x squared plus x minus 3. So we don't have to use the quadratic formula because here we have, again, a product that equals 0. And when you have a product that equals 0, that means one of the factors has to be 0. So you see now you've reduced this original formidable equation, right? You've reduced it to these two very simple equations, which you can solve, you know, just very quickly, right? X equals 1. Here we would have what? 2x equals -3 if we subtract 3 from both sides, or x is equal -3/2. Nice, there it is. There are 3 x-intercepts, 1 -3/2 and 0. So if you graph that function, I don't know if I have a graph of it, but if you graph that function, it will cross the x-axis 3 times, right? Did I make a graph of this one? No, I didn't. Too bad. All right, so wait a minute, let me look here. See if I have a graph in Desmos of this one. I don't think that's the one. Is that it? No, that one looks really bad, right? So that's not the right formula. Okay, so I don't have a graph of that one. Well, too bad. Okay, but we don't really need to see the graph, right? We already know without looking at the graph, right, what the three X-intercepts are going to be. What we don't know, of course, are what the two turning points are, or three turning points are, because it could have up to three turning points are, right? We don't know those, right? And without really looking at the graph, correct? But as I mentioned last time, that's what you're going to focus on in calculus is how do I find the turning points for this function with pencil and paper without having to use the estimate from a graph, okay? And strangely enough, it turns out to be almost the same problem. It's really the problem of finding X-intercepts again. Okay. So if we're looking for X-intercepts of polynomial functions, we are really, once you get above degree 2, right, you're really kind of, you're really kind of stuck with factoring, okay? I mean, you really need to be able to factor to find X-intercepts for polynomials. If you're not dealing with you're dealing with degree 3 or degree 4 or higher. So that's what we're going to concentrate on here is improving our factoring skills. So I'm going to show you now some techniques that you can use to help you factor polynomials better than just good old trial and error factoring, which is really what you've been using up until now to do factoring. So trial and error factoring is just, you try something and you see if it works, and if it doesn't work, you try another possibility, correct? Okay. And if the polynomial is not too complicated, if you just have a second degree polynomial, you can do that pretty quickly. So trial and error factoring is efficient. But if you get higher degree polynomials, trial and error factoring just becomes, just impossible, right? It just gets too complicated. So we have to learn some other methods, some little bit more powerful methods that will help us with factoring polynomials higher than degree 2. And we also have to accept the fact that sometimes we're just not going to be able to do the factoring. Okay, sometimes you just can't factor. Okay, so now what I'm going to teach you here first now is called the division algorithm. So it's an algorithm, it's a process, but an algorithm is a process, that you use to solve some problem. And so this division algorithm is the process that we're going to use to do some division. But we're not going to be doing division with numbers, right? Which is, of course, normally how you're used to doing division. We're going to be doing division with polynomials. So we're going to learn how to divide one polynomial into another polynomial, okay? But don't get too concerned, because it's going to work very similar to dividing one number into another, all right? So it's really very little difference. I want to take you back a little bit to grade school. I remember learning this in 5th grade, but I don't know where it's taught any longer, okay? But I learned it in 5th grade. So we're going to take a little detour here back to the 5th grade and remind ourselves of how to do long division with numbers, okay? So I wrote down a simple example here, and let's see if we can recall from 5th grade. This isn't always easy, but let's see if we can, because we've been out of 5th grade for a while. 5th graders could do this very quickly. Let's see if we can. That's like a TV show, isn't there? A TV show? Yeah, are you smarter than? Yeah. All right. So we're gonna see here today. All right. If we're smarter than a 5th grader. All right. So all right. So let's divide 23 into 329. Okay. So let's see if we can do that. And just to remind you of some terminology here, the number you're dividing by is called 23, it's 23, right? But it's called the divisor. And the number that you're dividing into is called the dividend. Okay, so there's divisor and dividend. So, and when you're doing long division with numbers, you know, by the way, there are other algorithms for doing this. So in different locations, learn different algorithms for doing long division, but I'm going to show you the kind of the American style. So, so we're going to write the divisor outside of this, you know, this bar here, right? And then underneath that, we're going to write the dividend, what we're dividing into. So, so let's put that there. So 23 divided into 329. Now, do you recall how you start this process? I'm trying to remember myself. I don't, kind of, Iris, but you're taking it, you're actually making it a little bit more complicated. In grade school, you always look to the digits on the left, right? So you're going to try first to divide 2 into 3, correct? Right? Okay. So again, you're going to have to put yourself back in 5th grade, right? So, yeah, I think we start with the 2 and we try to divide that into 3. Now, sometimes that won't work, right? And then, you know, you have to try something else. But in this case, fortunately, it does, right? So we can divide 2 into 3, and that goes in, what, 1 time? Is that right? Yeah, 1. So you put the 1 there above that division bar. And then before you subtract, though, you do something else first. And what you do after you have the 1 here, you have to multiply back. You don't remember that part? Yeah. You take the 1 and multiply it back times your divisor, right? Okay. And that gives you what, 23? Yeah. No, they couldn't have skipped that step, because if they skipped that step, you might have skipped that step, right? But they didn't. Because you have to have that step to know what to subtract, right? Because now you're right, Emil, we're going to subtract, right? So multiply back through, write this product here below the 329, right? And then we're going to subtract that. So what do we get there? What? 9? And then you bring this 9 down, right? Remember, you're bringing down the next digit. And then you repeat the process, okay? So it's a process. And part of that process is just repeating the process, right? Continually until you finish. So now, Emil, we're going to divide the 2 again into the 9. And that goes in how many times there? 4. Right. So you put the 4 up here, correct? And then, Emil, you have to multiply back through. I don't see how you can do this without multiplying back through. So you take the 4 times the 23. What does that give you? What now? 92, right? And then you subtract again, right? And that gives you 7. Now, you know, you're tempted to take the 2 and divide it into the 7. Okay, because you could do that, but we're not going to do that. We're going to stop. How do we know that we're stopping here at this point? So how do we know when to quit this? By the way, you don't have to quit. We could continue this process, but we could continue this process, and if we continue, it would have meaning if we continue. But here we're going to stop, because this is where you would stop in grade school. Why do you stop here in grade school? Do you recall? Well, I'm glad we reviewed this. Yeah. What about Fernando? What about this? This number 7 is called the remainder. And so what about that remainder? Yeah, well, look, all right, so here's key step. This is important. When the remainder is less than the divisor, you have to stop, right? Okay. See, 23 cannot go into 7, right? Okay. At least it can go in a whole number of times, right? So when your remainder becomes less than your divisor, that's the signal, usually in grade school, in 5th grade, to stop. Okay. So we would quit there. And what do we do with the remainder? There are lots of ways of writing your answer here, by the way. But often you would put what? Yeah, you would put a little r there with the 7, just to indicate that the remainder from this division is 7. What is that number? So the 23 is called the divisor. The 329 is called the dividend. What's the 14 called? You know what that 14 is called? When you divide one number by another, you get a what? Begins with a Q. Quotient. This is the quotient, and here is the remainder. Okay, so you get a quotient of 14 and a remainder of 7. That's one way of writing your answer. So what you know is, what your 5th grade teacher would have told you is, look, 329 is equal to 23 times 14. Right? Okay, so your original dividend is equal to your divisor times your quotient plus the remainder, because you got a little bit of a remainder here, right? Okay, 23 doesn't go into 329 an even number of times, so you got a remainder here of 7. So you know that 329 is 23 times 14 plus 7. The divisor times the quotient plus the remainder. That's one way of writing your answer. Another way is, here's another way of writing the answer that sometimes is given. Divide everything in this equation by 23. So when you do that, you get 329 divided by 23. I'm going to divide everything by 23. So I have 329 over 23 is equal to, when you divide 23 into this term, the 23's divide out, so you get 14 plus, and then 7 over 23. There's another way sometimes that answer is written. Okay. 329 over 23, that fraction is equal to 14 plus 7/23. Okay, plus an additional 7/23. So there's another way of writing the answer if you want to write your answer as kind of as fractions. Okay, right? Now, all right. So what was the point of all that? Because we really, fortunately, we don't have to do long division very often, right? Well, until now, because we're going to have to do long division now, okay? But we are not going to do long division with numbers like you did in 5th grade. We are going to do long division with polynomials. So I'm going to take one polynomial and divide it into another polynomial, okay? Like this picture, right? So I'm going to take a divisor polynomial, but this is a polynomial now, okay? So it has powers of x in it. And I'm going to divide that into some dividend, some polynomial that I want to divide into, all right? So I'm going to take a divisor polynomial and divide it into a dividend polynomial. What am I going to get from that? I'm going to get a quotient as my answer, okay? The quotient is also going to be a polynomial. Plus, I may have a remainder, because there's no guarantee that this divisor will go into this dividend an even number of times, okay? So you may get a remainder, but your remainder will also be a polynomial, okay? So we're just applying the same long division process that we were used to doing with numbers. We're going to apply it now to polynomials. Now, what that means is that your original dividend, okay, that's the polynomial you divided into, right? It's your divisor, this, times this quotient, plus the remainder. These two sides are equal to each other, right? So the polynomial you divided into should be equal to the divisor times the quotient, plus possibly a remainder. Of course, your remainder could be 0, because sometimes this divisor will divide evenly into the dividend, but sometimes it won't. So you'll get a remainder that's not 0. But still, you check your work by this times this plus this should be equal to what you divided into, just like here in arithmetic. This times this plus the remainder should be equal to this. So it's really just arithmetic. Another way of writing your answer, by the way, also, like we did with the numbers, is in this equation, if you divide everything by d of x, divide this by d of x, divide this by d of x, divide this by d of x, you'll come up with this equation. So p of x divided by d of x is equal to the quotient plus the remainder divided by the divisor. Just like it was in 5th grade, except here we have polynomials instead of numbers. The terminology, by the way, is the same as it was in 5th grade. Okay, this is the dividend. This is what you're dividing by. That's called the divisor. After you've done the division, you get a quotient plus possibly a remainder. All right. So all that sounds great on paper and abstract, but you have to try it, right? So until we've actually looked at an example, all of that's kind of not too concrete, right? So let's try an example. So I'm going to take this polynomial, 8x to the 4th plus 6x squared minus 3x plus 1, and I'm going to divide that by my divisor is going to be 2x squared minus x plus 2. So you're dividing this polynomial by this polynomial. What's the degree of this polynomial, by the way? 4. Degree here, 2, right? So I'm dividing degree 4 by degree 2. All right, so how are we going to write this down? Just like you do in grade school. Here's your divisor, and you're going to divide that into your dividend. And we're actually going to use exactly the same process. Now, there's one thing, though, I've got to caution you about here. When you're doing long division with polynomials, it's going to make your life much easier if you have every power of x from the highest power down to the constant coefficient. Make sure you have every power of x represented in both your dividend and your divisor. Both your divisor and your dividend, but it's really important to have it in the dividend, what you're dividing into. Let me show you what I mean. So what's the highest power of x here? Of course, it's 8x to the 4th power. But notice that in this polynomial, you skip a power, right? Because the next term is 6x squared. And then you have x to the 1st power. So this is going from x squared to x to the 1st power down to, this is a constant. So that's x to the 0th power. Remember, constants count as x to the 0th power. So we're missing x cubed. It will really benefit you to have the x cubed in your dividend. So the way you do that is you just put it in there, but you give it a coefficient of 0. Give it a coefficient of 0. So I need to leave myself a little bit of space here. So let me take the plus 6x, this, and let's shift that over just enough so that I can insert artificially another term here, which is going to be 0x cubed. It's also good to have that in your divisor as well, but that's less important. You really need it. Make sure you have all powers from the highest power down represented in your dividend. This one's okay, right? Because this is x squared, this is x to the 1st power, this is x to the 0th power. So you have 2, 1, 0, you have all powers of x there. All right, so that's just a little initial prep work before we actually start the long division process. Now, how do we start? Just like in grade school, take the leading term in your divisor and divide it into the leading term in the dividend. So you're not just dividing numbers here. Now you're dividing terms, okay, algebraic terms. But that's actually easier than dividing numbers. So I'm going to take, you can really do this in your head, but I'm going to write it down just in case you need it written down. 8x to the 4th over 2x squared. How does that reduce? So 8 over 2 is easy. That's what? 4. And x to the 4th over x squared. That's x squared, right? So our quotient here is 4x squared. So let's put that into our quotient. That's an x squared term, so I'm going to write it above the 6x squared here. It's again helpful to keep the powers of terms lined up. That will just help you not make mistakes here. Now, Emil, what do I do? What did you forget to do in 5th grade here that you're supposed to do? Multiply back through, right? Okay. So now you're going to take the 4x squared and multiply it back through. So 4x squared times 2x squared. I know what that is already because I just created the 4x squared, right, from taking 8x to the 4th, dividing it by 2x squared. So when you take 4x squared times 2x squared, you're going to get 8x to the 4th power. You just can't miss, right? Now take 4x squared times minus x. That comes out to be what? Minus 4x cubed. Make sure, again, you line things up properly. So that minus 4x cubed, I'm going to write it below the 0x cubed here. And then 4x squared times 2 is what? 8x squared. So put that there, and that's it. Yeah, Amanda. Yeah, we're multiplying back through. So 4x squared times 2x squared is 8x to the 4th power. 4x squared times minus x is minus 4x cubed. You have to multiply the 4x squared times everything.
Okay.
And then 4x squared times 2 is 8x squared. Now, Emil, what do we do at this point? Subtract. So we're going to subtract here, but subtracting with polynomials is a little bit different than subtracting with numbers. So to make it easier for me, I'm going to think of it as changing the signs and adding. So instead of subtracting, I want to think of it as changing signs and adding. That will make it easier for you. But changing signs and adding is the same as subtracting. So I'm going to make this a minus. I'm going to make this a plus. And I'm going to make this a minus. And now let's add. Okay. So 8x to the 4th, add minus 8x to the 4th. What happens? 0, right? Yeah, that should always 0 out. Otherwise, you've done something wrong. Okay. Now, 0x cubed and 4x cubed is what? That's 4x cubed, correct? And then 6x squared and a minus 8x squared. I think that's minus 2x squared, isn't it? And now, if you want, bring down your next terms. Okay. So you can bring down the minus 3x and the plus 1. Or you can think of those as adding them to 0. Same thing. Now repeat the process. So you're going to take 2x squared and divide it into 4x cubed. So if you can't do that in your head, just write it down. 4x cubed divided by 2x squared gives me what? 4 over 2 is 2, I think, and x cubed over x squared is x, right? So we have an x there. It's positive. So write positive 2x. Make sure you put the plus sign there because this is a polynomial. So you have to have the terms separated by signs. Now what? Multiply, right. So 2x times 2x squared, we know that's got to be 4x cubed. 2x times minus x is what? Is that minus 2x squared? And then 2x times 2 is what? 4x. Draw your bar across now and change your signs and add. So I made minus plus and plus minus. Add. So those go to 0, right? Oh, these also go to 0, don't they? I wasn't quite expecting that. But those go to 0. And then minus 3x minus 4x is how much? Minus 7x, and you can bring down the 1. Now, just like with when you're doing long division with arithmetic, there's always a question of when do I stop? Actually, you can continue this process indefinitely. You can continue this process indefinitely. And the answer that you get from that will have meaning. But we're not going to continue it indefinitely. We have to stop somewhere. And so, of course, in arithmetic, where do you stop? When the what? When the remainder is what? Then the divisor. But now, that less than concept doesn't have any meaning for polynomials, right, Amanda? I mean, how do I know when this is less than this? Okay, so not quite, all right. For polynomials, what we use for the idea of one polynomial bigger than another is degree. So you're going to stop when the degree of the remainder is less than, not equal, but less than the degree of the divisor. So what's the degree of minus 7x plus 1 as a polynomial? 1. What's the degree here? 2. That's less. Yeah. So that's it. We're done. So there it is. There's our quotient. 4x squared plus 2x is our quotient. And our remainder is, and you can put remainder just like you do in 5th grade, 7x plus 1. All right, so what have we learned from that long division process? Here's what we know. The original polynomial, the dividend, what we were dividing into, that is equal to this times this. The divisor, which is 2x squared minus x plus 2, times the quotient, which is 4x squared plus 2x, plus the remainder. Add on the remainder. So plus the minus 7x plus 1. You really don't need to put the parentheses there, but I'm going to put it there just to make it clear that this is the remainder, right? So the original dividend, what we were dividing into, is our divisor times our quotient plus the remainder. So unfortunately, this polynomial doesn't divide into this polynomial evenly, right? It doesn't divide in evenly because when we do division, we end up with what? We end up with a remainder, see, okay? So this polynomial does not exactly divide into this polynomial because when we do the division, we get a remainder. It is possible, though, for your dividend to divide perfectly into your, for your divisor to divide perfectly into your dividend. And in that case, you'll get a remainder of 0. So you can get remainder of 0 when you're doing long division with polynomials, just like you can with numbers, okay? And that's kind of the ideal situation because that means your divisor divides perfectly into your dividend, okay? Woo, fun. Let's try another one. I'll let y'all try one. I'm going to give y'all kind of a little bit simpler one, though. All right, so not so high powers. All right, so see if you can divide 6x squared minus 26x plus 12. Divide that by x minus 4. Okay. By the way, I want to point out something here. Okay, if you're, what's the degree of your divisor here? There's your divisor. Degree. What's its degree? What? 1. The degree here is 2. So you can start the process because remember, you'll end the process when your remainder has degree less than your original dividend. So if this had, for instance, degree 3, you couldn't even start. Okay, right? So you can't start with your divisor having bigger degree than your original dividend. That won't work. All right. But we're okay here, right? Degree 2 starting with degree 1. All right. All right. So see if y'all can set that up. Remember, it's going to look like this to start with. X minus 4 will go into 6x squared minus 26x plus 12. All right. By the way, check your powers here. This is power 2, and then this is power 1. and this is power 0, right? This is degree 2, degree 1, degree 0. So 2, 1, 0, that's fine. We have all of our degrees represented. Remember, if you skip a degree, you have to insert a term with a 0 coefficient, but we don't have to do that here. All right, so try that one, see what you get. I'm going to watch you. So you guys try that at home. This won't take very long. I think it goes pretty fast. All right, because these are not high degree polynomials to start with. Now do it again. Yeah, you can write it down. Also, okay.
Okay. Okay, so no, stop cheating. What? Oh, goodness. Oh my God. I remember from my last trying to make subtraction plus yeah. Yeah. Now, I mean, now add. Oh, yeah. So minus 2x. Now, what's the doesn't have I'll say yes, and we'll say less than I can't watch. And the first question is what? What? That's right. All right. Okay. So yeah, I could, and okay, let's try going through this one then. I need someone at home to guide me on this. All right, so y'all can talk or you can type, but you got to type fast. All right, y'all hear that at home? I want someone to describe to me the steps that I'm going to go through here to do this long division. Okay. Yeah, I'll send it in a second here. All right, so guys, y'all hearing me? Yeah, speak up.
So we would go into the 6x squared,
Right.
to divide that by x. So
Yes.
that'd be
So you take 6x squared and you divide that by x. Who's talking there?
Fernando.
Oh, Fernando. Okay. So you take 6x squared and divide that by x. What is that? What does that give you, Fernando?
6x.
6x, exactly right. So I'm going to write that right here. That's x to the first part. So I'm going to write it above the 26x here. Now, Fernando, what?
You would divide out.
Divide out. Nope.
Multiply. Sorry.
Multiply, right. So take the 6x and multiply it back through the x minus 4. So what does that give me?
That'd be 6x squared and 24x.
Yeah, minus
24x.
24x, right?
Because
6x times the minus 4 is minus 24x. Now
we
what?
will switch the signs.
Switch the signs and add. That's the same as subtraction. So add these two, they cancel. What do you get here?
Negative 2x.
Minus 2x, and then you can bring down the 12. All right.
Now repeat the process, right?
Mm-hmm.
So now what do you get?
-2. I
Yeah,
mean,
x into minus 2x is minus 2, right? X into minus 2x is going to give us minus 2, right?
mhm.
Now multiply back. So minus 2 times x is minus 2x, as what we expected. And now minus 2 times minus 4 is plus 8, right?
Mhm.
Now
Switch the
again,
signs and
switch the signs and add. So you end up here with these two terms canceling, right? And then 12 minus 8 is 4. Now what, Fernando?
Because now you would set that as a remainder, so it'd be
Yes. So we
4
know we
over-
have a remainder of 4. Why do we know we can stop there, Fernando, with a remainder of 4?
because there are no longer any x values that can be divided.
Okay, that's not quite it. All right, all right. Intuitively, that's correct, Fernando. You're right. But the real reason is, as a polynomial, because we're thinking of all of these things as being polynomials. As a polynomial, what is the degree of a constant like 4?
0.
0, right. Constants as polynomials have degree 0. So this is degree 0, but what's the degree of the divisor?
1.
1. So this degree is less than this degree. I mean, sorry, this, yeah. The degree of the remainder is less than the degree of the divisor. So that tells us we can stop, all right? Degree 0 less than degree 1, so we can quit. So there's our answer. If you divide x minus 4 into 6x squared minus 26x plus 12, you get 6x minus 2, but with a remainder of 4. So one way of writing that out is, well, there's a couple of ways of writing it down, right? We know that 6x squared minus 26x plus 12, we know that's equal to the divisor, x minus 4, times the quotient, 6x minus 2, plus the remainder. Or another thing we know is if you take 6x squared minus 26x plus 12 and divide it by x minus 4, you will get 6x minus 2 plus, and then you can take your remainder and divide it by your divisor. Okay, so this fraction, 6x squared minus 26x plus 12 over x minus 4, that simplifies to 6x minus 2 plus 4 over x minus 4. Now, what we're hoping for, what we would really be hoping for is to have a remainder of 0. We would really like to find one polynomial that goes into another polynomial a whole number of times, an even number of times, so that we don't get a remainder. And I'll explain to you now why having a remainder of 0 would be useful to us. Okay. All right, but before we do that, let's take a little bit of a break, and then I'm going to make your life easier by showing you a little shortcut for doing long division that makes the long division go faster. All right, this is called synthetic division. So this will speed up this long division process considerably. All right. Okay. So let's stop there for a moment, though, and then we'll come back and I'll show you this shortcut. You're going to like it. It's easy. Okay, let's resume. And all right, so everybody at home, we're resuming, and I promise you the shortcut for carrying out long division, which is called synthetic division. Synthetic division works if you have a divisor of, so it's got to be a very simple form. If you have a divisor of a form x minus a constant. So if you don't have your divisor of the form x minus a constant, then you have to do full long division if you want to divide by that divisor. But if you have divisor of the form just x minus a constant, then you can do this simplified algorithm for long division called synthetic division. So let's repeat that problem from before, except let's do it using synthetic division. You're going to see it goes faster. And the reason we can do that is, remember the divisor from the previous example, we were dividing by x minus 4. So we just had x minus a constant, right? Okay, so that's of the proper form. By the way, synthetic division also works if your divisor is of the form x plus a constant instead of minus a constant, because you can write that as x minus c, right? X minus a minus c would be x plus c, and see that's still of the form x minus a constant. So you can use synthetic division also with this form of divisor as well. All right, so but we've certainly in good shape for this example. So let's go through the synthetic division process. What you want to do is, in your divisor, since it's x minus a constant, take the constant that's being subtracted from the x and write that down, okay? And then I'm going to write beside it, I'm going to kind of segregate it here with this, this symbol, just to distinguish it from what I'm going to write on the rest of this top line, which is the coefficients of my dividend, what I'm dividing into, right? So I'm dividing into 6x squared, so you write down the 6 and the minus 26 and the 12. You don't have to write down the x's, just the coefficients. So we're really going to kind of get rid of the x's there momentarily. Make sure, however, that before you start writing down the coefficients, make sure that you have all powers of x after the highest power. Make sure you have all powers of x there, okay? So if you were missing some power of x, you need to insert it with a coefficient of 0. I think that comes up, yeah, that comes up in the next example. So we'll demonstrate that in the next example. All right, so you see what you did there? You just put the coefficients of the dividend, and then there's the part of the divisor there, right? The constant part of the divisor. And now I'm going to draw another bar here because we're going to be doing some adding, okay? All right, so here's how this starts. Bring down the 6. Bring down the 6. So bring down the 6, and then multiply it by the 4. That's, of course, 24, right? Write it here. So 4 times 6, 24, put it there. Now add. You're always adding in this process. What's minus 26 plus 24? That's what, 2, right? Multiply again. 2 times 4 is 8, right? Okay. And then, is that the same problem? What did we do? What is off there?
It's a -2.
Oh, it's -2. Yeah, okay. I added wrong. All right. Okay. We had to come up with the same answers before, so I was wondering what I did. Yeah, minus 26 plus 24 is -2. Sorry. All right. And then 4 times -2 is -8. That works, right? 12 times -8 is 4. And that's it. All right. So we know we're going to quit. Now, all right. So what do I know my answer is here? All right. Well, there are the coefficients of your answer. Okay. So you know your answer is going to be 6x minus 2. And then this last value you get is still the remainder. So when you divide x minus 4 into 6x squared minus 26x plus 12, there's your quotient, 6x minus 2. And then there's your remainder is 4. So always keep in mind that the remainder is the last value. That's not going to be a coefficient of your quotient, right? That was pretty fast, right? See, that went really quickly. Just addition. and some multiplication, which unfortunately I did wrong, right? Well, I did the addition wrong here. So just be careful about your arithmetic, okay? But other than arithmetic, it's easy. All right, let's try another one, and then I'll give you one. So I'll do half of this problem, and I'll let you do half of it. So we want to take 2x cubed minus 7x squared plus 5. All right, and let's divide it by both x minus 3 and then by x plus 3. All right. Now, both of these divisors, right? Both of those divisors are of the right form because you have either x minus a constant or x plus a constant. So you can always use synthetic division if your divisor looks like this. By the way, you cannot have a coefficient on the x here, though. So be careful about that. All right. It has to be just plain x and then plus or minus a number. All right. Well, let's start first by dividing by x minus 3 into the 2x cubed minus 7x squared plus 5, right? So let's see, what do I do? So to set up the synthetic division, there's your sort of synthetic division bar there. What do you put on the left-hand side of that? A 3, right? Because you're dividing by x minus 3. So the constant you're subtracting from the x is 3. So that's what you put. And then just put the coefficients of the dividend what you're dividing into next. So there's 2, and then there's minus 7. But be careful here. Notice you don't have an x to the first power term, right? It's missing. So you're going to give that a coefficient of 0. Be careful to not leave that out. See, minus 7x squared plus 5, that would be the same as plus 0x plus 5. And you have to have all of your powers of x after the highest power, you have to have them represented. So here's third power, second power, first power, and then a constant. And then, of course, the 5, right? Okay, so draw your addition bar across now, and then where do we start? Bring down the 2, right? So that kicks off the process. Just bring down the 2, and then everything else here is kind of goes fast. 2 times 3 is what? 6, right? Okay. Add and you get what? -1. 3 times minus 1 is -3. Add, you get what? 3 times minus 3 is -9. Add, you get what? -4, right? Okay. So you know your remainder. Your remainder is going to be -4. What is the quotient then? See, there's the divisor, there's the dividend. So what's the quotient? What's the actual answer to the division problem? That comes from these values. So yes, 2x squared minus x minus 3. So what did this tell us, right? Okay. So what did this tell us? This tells us that what? Our original dividend, 2x cubed minus 7x squared plus 5, that's equal to our divisor, which is x minus 3, times the quotient, which is 2x squared minus x minus 3, plus this remainder of what? -4. So if you take x minus 3, multiply it by this, 2x squared minus 3, 2x squared minus x minus 3, and then add on this remainder, that would give you 2x cubed minus 7x squared plus 5. Now, I want to show you something here. that's useful about synthetic division. Let's think of this. So this polynomial that's our dividend, the 2x cubed minus 7x squared plus 5. Let's give that a name. So I'm going to call that p of x. And suppose, just for some reason, you wanted to evaluate p of 3. Suppose you had that task in front of you. You had to compute p of 3. Of course, you could do it from the formula, right? And so you would get what? 2 times 3 cubed minus 7 times 3 squared plus 5, right? What does that turn out to be? 3 cubed is 27, right? Times 2 is 54. And then minus, what, 7 times 9? 63, is that right? And then plus 5. So what do you get? Minus 4 out of that? So you end up with minus 4. So for this function, if you use an input of 3, you get a y value of minus 4. Notice that that turns out to be the same as this remainder. That's the same as this remainder. Why is that? Well, because look, p of x, this formula, right? You know this formula is the same as this, correct? It's x minus 3 times 2x squared minus x minus 3 minus 4. So if you use this version, see, that's equal to p of x, right? But if you use this version of the formula for p of x to evaluate p of 3, notice what happens. If you plug 3 in for x into this expression, I don't know what happens when you plug 3 into these parentheses, but what happens when you plug 3 into this parentheses? It turns into 0. So all of this gets zeroed out, and what do you end up with? Just the minus 4, right? So it's much easier to evaluate this polynomial at 3 using this formula than it is to use the original formula. We're going to look at that again here in just a second. All right, I'm going to let y'all try this one now. Okay, so same thing. I want you to use synthetic division to divide, same thing, 2x cubed minus 7x squared plus 5. I want you to divide it, instead of by x minus 3, let's divide it by x plus 3, however. Okay, so how are you going to set that up? You have to think of the x plus 3 as x has to be minus a constant to use synthetic division. So x plus 3 is the same as x minus what? See, x plus 3 is the same as x minus negative 3, right? Okay. Isn't x minus a minus 3 the same as x plus 3? So when you're doing the synthetic division now, you're not going to put a 3 here. You're going to put instead what? Negative 3, right? Okay. All right. So try that. And tell me what happens. I'm not sure what the answer is going to be, right? So divide the 2x cubed minus 7x squared plus 5 divided by x plus 3, but using the synthetic division. It goes super fast, right? Okay. Synthetic division is really fast. In fact, it's famously fast. That's okay. That's a big number. But even if it's a big number, remember, all you're doing in synthetic division is multiplying and adding, right? So you're not doing a hard arithmetic, okay? So division, for instance, right? Right. It's going to be an homework. We're going to be on the test with big number. All right. Same process. Negative. Some people are going to. All right, let's see what we got then. So let's try this. And so I can really keep the same setup, right? Let me just erase some of these some of the prior answers. And now this is going to be a minus, right? Instead of a plus. So see how the arithmetic works out now. So bring down the 2. So you have 2 times minus 3 is minus 6, right? Minus 7 and minus 6 is minus 13. Minus 3 times a minus 13 is positive 39, right? And then minus 3 times positive 39 is what? Minus 117. Add and we get what? Minus 112. Okay. All right. So we know then that 2x cubed minus 7x squared plus 5 is equal to x plus 3 times what? Different quotient here, right? Did I? Okay. Yeah, I think maybe you added a negative, right? Okay. All right. So we know that 2x cubed minus 7x squared plus 5 is x plus 3 times 2x squared minus 13x, right? And then what? Plus 39? And then, but with this large remainder now of minus 112. So, by the way, that now tells us, now, if you want to evaluate for this function, 2x cubed minus 7x squared plus 5, if you wanted to evaluate p of minus 3, you could do that, of course, by plugging the minus 3 into the formula. But you could also do it by looking at this synthetic division. What is p of minus 3? You know it automatically is what? Minus 112, right? It's going to be minus 112. So that's actually the very next statement. What I just told you there is actually the very next statement in the notes, all right? This is called the remainder theorem, okay? So what the remainder theorem says is if you have a polynomial, this only works for polynomials now, okay? If you have a polynomial, some polynomial, but that could be a complicated polynomial, right? That could be a really high degree polynomial. If you want to calculate P of C, where C is just some constant, so you want to evaluate that polynomial at some constant, right? Of course, one way to do that is just take the constant and plug it into the formula for P, right? So you could grind away and, do the multiplications and additions. But the other way to evaluate P of C is to carry out this synthetic division. Divide your polynomial by x minus C You can do that with synthetic division. And whatever the remainder is, that's going to be the polynomial value at C. Okay. So the remainder theorem gives you an alternate way of evaluating polynomials. Now, you might think that's not, okay, that's kind of a curiosity, right? But is that really useful? Well, let's try that and see. So suppose we've got this big, ugly, polynomial here. 3x to the 5th power plus 5x to the 4th power minus 4x cubed plus 7x plus 3, right? And we want to evaluate p of minus 2. So we want to calculate p of minus 2, right? So, that's, in one sense, that's a very straightforward problem, right? You can just take minus 2 and you could plug it in to this formula. But that's easier said than done, right? You can write it down, but that's not an easy computation to carry out. Because, you have to raise minus 2 to the 5th power, and you have to, multiply by 3, and then you got minus 2 to the 5th power, to the 4th power times 5, and then you have to add all these, terms together. Okay, so that's going to take a little bit of work. But our alternative here is to use synthetic division. Okay, so what the remainder theorem says is, if you want to evaluate p of minus 2, just use synthetic division with the constant minus 2. Let's see, what are my coefficients here? 3, 5, minus 4. Whoops, what's missing there? Yeah, so put in a 0 for the x squared, right? And then a 7, and then a 3. And now do synthetic division. So bring down the 3. There's minus 6, right? 5 and a minus 6 is minus 1. Multiply that gives us what? 2. Minus 4 plus 2 is minus 2. Minus 2 times minus 2 is positive 4. 4 times 0 is 4. Minus 2 times 4 is what? Minus 8. 7 minus 8 is minus 1. Minus 2 times minus 1 is 2. 3 and 2 is what? 5. So guess what? P of minus 2 is 5. If you do all of this arithmetic with your calculator, you're just going to get 5. Okay, all of that just simplifies to 5. Well, I don't know if I believe that. I'm not convinced that's right. Let's try it here. What's minus 2 to the 5th power? I think that's minus 32. Plus minus 2 to the 4th power is 16. So you have 3 times minus 32 plus 5 times 16. Minus 2 cubed is minus 8 times a minus 4 would be plus 32, right? Minus 4 times minus 8 is plus 32. Minus 14 plus 3. Do all those numbers add together to give you 5? 3 times a minus 32 is minus 96. All right, minus 96 plus 5 times 16 is 80. Is that 5? Yeah. That also turns out to be 5. But that takes a little while, right? Okay. That takes quite a little bit of computation. Here, I think it was very simple to 5. So synthetic division gives us a shortcut for evaluating polynomials, right? We can evaluate polynomials, by brute force, by plugging numbers into the formula for the polynomial, but we can also evaluate polynomials by using synthetic division. Okay, now, why is that useful? Because, how often do we have to evaluate polynomials anyway? Well, the answer is you as a person don't really evaluate polynomials that frequently, okay? But your calculator and computers evaluate polynomials a lot, okay? Because they use polynomials to simulate other functions, like trigonometric functions or exponential functions or logarithmic functions, all right? So when your calculator is evaluating sine or cosine of a number, it's really not evaluating the function sine or the function cosine. It's evaluating a polynomial function that's an approximation for sine or cosine. Okay. Now, why does your calculator do that? Because what sort of calculations do you have in polynomials? What sort of arithmetic operations do you have in a polynomial? Well, you've got addition and subtraction, right? And you've got powers. Of course, powers are really the same as what? Just what? What's x to the 5th power? That's really what arithmetic operation? Isn't that just multiplication, right? So you really just have addition, subtraction, and multiplication in polynomials, right? You just got addition, subtraction, and multiplication. And on a computer, that's really all you can program is addition and subtraction, really just addition and multiplication, okay? When you program the CPU of a computer, that's really all it does is addition and multiplication. So the computer or the calculator is forced to use polynomials to help it compute more complex functions like sine and cosine. And so calculators and computers evaluate polynomials quite a lot, okay? And because they do it a lot, they have to do it fast, all right? They have to be able to do it fast, otherwise you're going to be waiting too long to get your results. What allows them to evaluate polynomials quickly? Oh, this idea, okay? The synthetic division, much faster, all right, than just brute force evaluation of polynomials. It's going to help us too. All right, I want y'all to try this one now, okay? So this is pretty easy to do by hand. We want to, for this polynomial, x cubed minus 7x plus 6, I want you to evaluate p of 1. Now, you could do that by hand pretty quickly, but let's do it with synthetic division, all right? So evaluate p of 1 for me using synthetic division. So what is p of 1 going to be? This is more practice with sure you get all the coefficients proper. Well, that one worked out nice. Remainder of 0. Remainders of 0 are always nice, right? That tells us something about our vision. The remainder. Right. Okay, well, it's just this. It's just a thing. So you take x squared. 7, 6. Down. I remember sort of. Okay. Right. Yeah, all right. That's all it is. That is easy. Learn class. Yeah. You have to use what? Yeah, it's problem number 2. Okay, so just ignore. Okay. Yes. All right, so also this one is I see why I put this example in here now. Okay. So if we try to evaluate P of 1 using synthetic division, right? So my coefficients are going to be 1 and then 0 because we're missing x squared. So don't forget to put in there that in there. If you leave that off, you're doomed. And then a -7, right? And then the +6, correct? And now let's start our process. So bring down the 1, and then 1 times 1 is 1. Okay, that can be easier than that, right? 1 plus 0 is 1. Again, am I doing this right? And so 1 times 1 is 1 again. And now -7 times 1 is -6. 1 times -6 is -6. Oh, and now we end up with a remainder of 0. That's very useful to know. All right, so what is P of 1? 0, which tells me what about the number 1 for this polynomial? What is the number 1? That's a special number for this polynomial. That's a what? So yeah, so when you use an input and you get an output of 0, what is that input better known as there? So if I make a graph, what's going to happen here when I graph this? What's going to happen at the number 1? So, you know, that's polynomial graph, right? Polynomial graphs are nice and wavy, right? Probably nice and wavy like this, okay? But what happens at x equals 1? Huh? No, it never turns into a line. No. Yeah. So, you know, just thinking about this. So it's wavy, right? I don't know how many waves it's got there, but what happens at 1, right there at 1? It hits the x-axis, right? Okay, so what's that called then? A 0, or what are our other names for it? A root, or a, in that picture, what would you call that? X-intercept. Yeah, well, boy, y'all are really yes, 1 is an x-intercept, right? Because the matching y value is 0. 1 is an x-intercept, right? Oh, so look, when we did synthetic division and we got remainder 0, we have found an x-intercept, right? Or our alternate names are 0 or a root, right? But oh, we know much more than that. So we know that x cubed minus 7x plus 6, you can write that as the divisor, which is x minus 1, times the quotient. What's the quotient here? X squared plus x minus 6, right? Plus the remainder, which is what, however? 0. So you don't have to write in there the plus 0. Oh, so look what you have done. You factored. You were able to factor x cubed minus 7x plus 6. That is factored now. It factors as x minus 1 plus x squared times x squared plus x minus 6. If we had a remainder, it would not be factored. Okay? But without the remainder, oh, we've done managed to factor this. Okay. Now that was just trying to stroke them up, right? But I've got this now factored. Actually, now I have a chance of completely factoring, because can you factor x squared plus x minus 6? Maybe able to factor that. I think you can, because that's not too complicated, right? So how does x squared plus x minus 6 factor? X what? No, I think it's x plus, isn't it x plus 3, x minus 2? Yeah, it's x plus 3 times x minus 2, right? X times X is X squared. 3 times minus 2 is minus 6, right? And then you have 3X minus 2X is positive X, right? Oh, so, oh, I found that one factor. That was just kind of luck, right? Okay. So I found this one factor, X minus 1, by synthetic division. And now, because this is just a quadratic second degree, I can factor that just by inspection. So I get it. Now it's completely factored. X minus 1 times X plus 3 times X minus 2. So what are the other X-intercepts? So my picture here is not that bad. What are the other X-intercepts? Minus 3. So you have an X-intercept over here at minus 3. And what's the other one? Up here at 2. Okay. So maybe that's kind of close to the picture of what this graph of this polynomial looks like. Of course, it could be going down and coming up again. So I may have it inverted there. All right. But maybe the graph looks something like this. Oh, so now I know all of the X-intercepts, because how many X-intercepts can this thing have? Only 3, right? Okay, because it's degree what? 3. So it can only have 3 X-intercepts. Oh, nice. Okay, well, we reached a good place to stop there. All right. Okay. So wow, there now we saw one example of we used synthetic division with a little bit of luck there. Now we were able to use synthetic division to factor this polynomial, and I can tell you before we were not able to factor this. Okay, x cubed minus 7x plus 6, we would not have been able to factor that. All right. Yeah, Jed. Oh, okay. So let me pass this around. All right. Okay, guys. All right. So oh, we made a lot of progress today. Okay. Synthetic division is really useful in helping us now factor polynomials. That was our goal when we started. The one thing that's a little bit discouraging in that example is I told you the one to start with. How would you have known to start with the number 1 there, though? We'll learn about that. Okay. So I'm going to stop there.